Alright, thanks for watching and welcome to the cool zone. So today we'll focus mostly on the wave equation, which is really neat PD. Alright, ask away. I'm so cool. Okay, number 9 in section 2.1. I can't read, sorry. Oh yes, that's a great question. So the question is solve a wave-like equation which is uxx minus 3uxt and then minus 4utt equals 0 with the initial condition x squared and the initial velocity ut, basically I believe e of x. Okay, then the approach is, by the way, that's a very legit question for the exam. Don't just assume I'll give you the wave equation. So the idea is just similar as the wave equation, namely, how would you factor out x squared minus 3xt minus 4t squared? Again, I'm really bad at those things, but I believe it's something like x minus 4t and x plus t. And we try out x squared minus x squared plus xt minus 4. So that works. So in other words, this thing, d squared over dx squared minus 3 d squared over dx dt minus 4 d squared over dt squared, you can actually factor this out as d over dx minus 4 d over dt and d over dx plus d over dt. So essentially, what this equation says, it's the same as d over dx minus 4 d over dt applied to d over dx plus d over dt u equals 0. Just like for the wave equation, except, we have, it's called, we don't have this x minus ct, but it's okay. So basically what you do, you let this be v, and then you have d over dx minus 4 d over dt v equals 0. And then basically vx minus 4 vt equals 0. And so I believe, let's see, oh god, vxt equals any function. This is like x plus, I keep forgetting. How embarrassing. Let's see, x minus c, yeah, it should be, well, maybe, let's see, x t minus 4x, so 4x minus t. Again, it's just a transferred equation I'm blanking out, but let's see, that should be 4, let me just check. So Vx is 4f prime of 4x minus t. Vt, it's minus f prime 4x minus t. No, so it might be the other way around. So t minus 4x plus t. No, wait, sorry about that. 4x plus t. I think that's the correct one. Because yeah, if you differentiate, I know it's so embarrassing, but if you differentiate that, so if you do vx minus 4vt, that becomes 4f prime, and then minus 4f prime, and that gives you 0. Very good. So we have that. Sorry. sorry, I know. I have like this very short-term memory. But anyway, so if you plug this into the formula for the transport equation, you get this. And then lastly, what you want to do, you want to use the fact that v equals d over dx plus d over dt u. So in other words, ut plus ux equals v. So ut plus ux equals this gibberish, right? F of 4x plus t. Okay, and this is an inhomogeneous transport equation. And the way to do it, you first guess the homogeneous part. And you first solve the homogeneous part, and then you guess a particular solution. So to solve ut plus ux equals 0, that just gives you uxt equals, let's say, again, transport equation, let's say g of x minus t. So that's the homogeneous one. Well, for the particular one, if you want to have, so that's your homogeneous solution. For the particular solution, we'll do it sort of like what we guessed. Do it sort of like what we guessed for the wave equation. So we basically say, how about we guess uxt? It's first of all an antiderivative of f, but let's just guess an extra constant. So that's what I did very badly in lecture, but I modified that in the notes. And then, well, let's calculate ut plus ux. That's a times f of 4x plus t plus a times, so with respect to t, plus a times f of 4x plus t with respect to x. And that just gives us a times f prime of 4x plus t times the derivative of that with respect to t, which is 1, plus a times f prime of 4x plus t times the derivative of 4x plus t with respect to x. So using the chain loop, and then you basically get 5a, and then a derivative of capital F prime, it's just little f, 4x plus t, and ideally you want this to be f of 4x plus t. So you basically just compare. You guess that 5a equals 1, which gives you a equals 1/5. So what does it tell you? It tells you a particular solution is just 1/5 capital F of x 4x plus t. So how do you find the general solution? You just add up this solution with this solution. So u of xt equals to basically the homogeneous solution plus the particular solution, which basically tells you, this is arbitrary as well, and so you get uxt is just some arbitrary function. Let's see, arbitrary function of 4x plus t plus some arbitrary function of x minus t. Comment, yeah, and I'll do the other problems too. Now, this is good, except we just need to solve, for the initial conditions, but that's not too bad. So I guess u of x, I hope it's not too bad. U of x0, that is, so f of 4x plus g of x, and we know that's x squared. On the other hand, let's differentiate this. So ut of xt, well, that's f prime of 4x plus t minus g prime of x minus t. And particular ut of x0, then of 4x, minus g prime of x. And we know that is e to the x. Whew. And then basically, you integrate this just like it did in lecture. So we get f of 4x minus g of x equals the integral of this, so e to the x plus a constant. And then you get two equations. So f of 4x plus g of x equals x squared. And then f of 4x minus g of x equals e to the x plus a constant. And then you just solve for all the shebang. Then, so adding those two equations, you get 2f of 4x equals, so x squared plus e to the x plus the constant. So f of 4x equals, so x squared over 2 plus e to the x over 2 plus a constant. And look, if f of 4x is that, f of x is just the whole thing, you know, where instead of 4x, you just divide everything by 4. So x over 4 squared over 2 plus e to the x over 4 over 2 plus a constant. And that gives you x over 32 plus e to the x over 4 over 2 plus a constant. Oh, I forgot. I think constant over 2. My bad. And then to get g, you just subtract the 2. So basically to get 2g of x equals x squared minus e to the x minus c over 2. So g of x equals x squared over 2 minus e to the x over 2. So I don't know what I'm thinking. Minus c over 2. And then last but not least, you just use the solution, and then I forgot what they were, but I think it's like u of xt. I think it's f of, I think 4x minus t, plus g of x minus t, either minus t or plus t. I feel it's plus t. Okay, no, it was minus, sorry. Okay, and then what we end up, we just plug in all this shebang, so 4x minus t over 32 plus e to the 4x minus t over 4 over 2 plus c over 2, and then plus x minus t squared over 2 minus e to the x minus t over 2, and then minus c over 2. This cancels out, and you get the general solution of this. Woohoo! Okay, 2.1 number 10. So, well, 2.1 number 10 is just like 2.1 number 9, but you just factor this out this time as like x squared. X squared plus xt minus 10t squared, and that just becomes, I think it's, let's see, it sounds like x minus, how do you factor that out? Minus 20, okay, that makes more sense. No, I don't know if it makes more sense, but could it be like something x minus 5t? Or I guess x plus 5t times x minus 4t? Yeah, so you get that, and then again, you just apply the exact same process, except I think the only thing that changes, you replace g and f and like the right-hand side by phi and psi, and then you just proceed like you do in lecture. Okay, and then let's see, the process, yeah, okay, so why, the question is, why is the x partial derivative of f the same as a t partial derivative of f? Well, not quite, because I think we had f of 4x minus t. So I think I understand what you're trying to say. So f is just a function of one variable. So careful, you don't really use the chain rule or the chain rule. You just use the ordinary chain rule, which just says to differentiate this with respect to x, you differentiate this function, which is a function of one variable. So it would be f prime of 4x minus t. And then you differentiate the inside with respect to x to get the derivative of 4x minus t, which is 4. So picture-wise, the way to picture it is, let's say f depends on y, which depends on x and t, where y is 4x minus t. So to differentiate this with respect to x, you get that if you want df over dx is df over dy, which is just f prime, times dy over dx, which is the derivative of this with respect to x, which is just 4. Okay, let me see. AP1, I forgot. What was A? Oh, yeah, AP1 was that the chain rule question? Let me see. I'll be back, don't worry. Yeah, I think AP1, okay, I'll get back to your questions, don't worry about it. Well, I do have I have time, okay. Also, yeah, so one question was, since f and g are arbitrary, is it possible that there are lots of solutions? Yeah, for the general solution, it is possible. But you see, now we found f and g, so it turns out here there's just one solution. And in fact, that's what we kind of hinted at last time. It's with those energy methods, you can actually show that given any initial conditions, you just have exactly one solution. And in fact, that's what we did. Okay, so I think maybe it switched the two, but I think AP1 was just saying if you let xi equals x minus ct and eta to be x plus ct, then basically the question is calculate utt in terms of xi and eta. So, and well, you just use the chain rule, so the chain rule. So let's calculate du ut, which is du over dt. Now again, u depends on x and t, which depend on xi and eta, which depend on xi and eta. So, well, no, it's the opposite, sorry. U depends on xi and eta, which depend on x and t, which depend on x and t. So, to calculate ut, you first do du over dxi over dt, plus du over deta over dt. And then basically you get u xi, and then derivative of xi with respect to t, it's minus c, plus u eta, derivative of eta with respect to t, that's c. And so you get c times u eta minus u xi. That's one thing. And now we just have to do this again. So now let's do partial ut, so utt. That's partial ut with respect to t. So that's partial ut with respect to xi, partial xi with respect to t, plus partial ut with respect to eta, partial eta with respect to t. And now we know what ut is, so this partial really c u eta minus u xi with respect to xi. The xi over dt, it's minus c. And then plus partial, again, c u eta minus u xi with respect to eta times the eta over dt, which is c. And then, I know, so much math today. The problem is it's partial differential equation, so lots of partial derivatives. So what we get, it's minus c squared. Because we have this minus c and we have this c, then d, so u eta with respect to xi, u eta with respect to xi, minus u xi xi, plus, again, c times c, so c squared, and then u eta with respect to eta, minus u xi eta. And if you calculate that, you get basically c squared u xi xi minus c squared u xi eta. Eta xi is xi eta in terms of partial derivatives, plus c squared u eta eta minus c squared u xi eta. Those come together and we get c squared u xi xi minus u2 u xi eta plus u eta eta. Okay. What do you mean how you can add the x? I'm kind of confused what you mean. How can you add the x derivative of f and the t derivative of f when solving a particular solution? Well, I think that was just I'm a bit confused about that question. Oh, I think you were saying about that when we calculate, I think ut, something like ut plus ux, and then we want this to equal to f of, I think, x minus 4t. Why are we adding this? Well, because we're plugging in u to be a of f of x minus 4t with respect to t plus a times f of x minus 4t with respect to x. And that's because we're just guessing that u has this form and we just plug it into the equation. That's what we're adding it. We're just adding it because that's what the PDE says. There's no intrinsic reason for that. Okay, well, let's see. There were other questions. Okay, so I did. All right. That's a lot of fun question. Okay, so 2.2 number. Oh, how nice is it? The question already tells you the energy. I might not be so nice on the exam. So, you're so lucky. You have so many awesome questions in that class. Okay, so suppose you have the energy as follows, which is 1/2 ut squared plus ux squared, and then whatever this term is, momentum density, whatever that means, p. And the question is, well, we have to show that if you differentiate e with respect to t, you get the derivative of p with respect to x. So let's just calculate that. d e over dt is just the derivative of this thing, ut squared plus ux squared with respect to t, and then you literally Chen Lu the hell out of this. So it's 1/2 times the derivative of this with respect to t, so 2 utt plus 2 times the derivative of u with respect to x times uxt. And that really becomes, so utt plus uxt. So that is dE over dt. We want to show that it's dp over dx. Well, let's differentiate that with respect to x. Sorry, x. And then what you get is, using the product rule, utx ux plus ut uxx. And let's see, well, let's compare the two terms. So those terms are the same. And well, those terms are the same provided utt equals uxx. But remember, I think u solves the wave equation with c equals 1. So by definition, utt is uxx. So you get this, dE over dt. And then you can also show, similarly, that dp over dt is dE over dx. And lastly, we need to show that E and P solve the wave equation, satisfy a wave equation. Well, let's calculate ETT. And that's super cute. So ETT, it's ETT. ET wants to go home, but ET is just PX. So that's PXT, and that's PTX. But from the other problem, we know that PT is PX. Wait, so, wait, I'm confused. No, PT, I think it's EX. Okay? X, and we get EXX. So ETT is EXX. So E also solves a wave equation. Okay, and then number 5. Yeah. Okay, how adorable is this problem? Okay. Number 5. So for this damp string, so which I don't know what that is, but I think it says equation 3 in 1.3. So this thing, UTT UTT minus c squared uxx plus RUT equals 0. And it says show that the energy decreases. And well, there's two ways of doing it. Suppose you have the energy, you just calculate then the derivative with respect to time, but that's like for wusses. Let's instead use again that energy method I talked about. So just like for the wave equation, let's multiply this equation by ut and then see what's going on. So then we get, so utt minus c squared uxx plus RUT, all this times ut equals 0 times ut. And that's just 0. And then what we get is UTT times UT minus c squared UXX times UT plus R UT squared equals 0. And then just integrate with respect to x. So from minus infinity to infinity dx, integral from minus infinity to infinity dx, and integral from minus infinity to infinity of this dx. Now, just like for the wave equation, notice this is really 1/2 d over dt ut squared. And you integrate that with respect to x. This one, you integrate by parts. So you put the x on the other side. And again, assume the boundary terms go to 0. So assume everything is 0 at plus or minus infinity. So what this becomes, it's minus c squared times minus integral from minus infinity to infinity of ux, uxt, dx. And well, this term which we don't really know what to do with. R integral from minus infinity to infinity of ut squared dx. Very good. And then remember how I told you it looks scary the first time, but the more you do it, the less scary it is? Let me just find some markers. Because I think the second time you see it, it's not too bad. Because notice, so what happens here is that what we get is d over dt. If you want 1/2 d over dt, integral from minus infinity to infinity of ut squared dx. And then this is plus c squared, integral from minus infinity to infinity of uxt dx, which you can write also as a derivative, again 1/2 d over dt, ux squared. And still this gibberish term, which seems weird, r integral from minus infinity to infinity ut squared dx. Good. Again, you have a plus, that's very important. And this just becomes, it's d over dt of 1/2 integral from minus infinity to infinity of ut squared plus ux squared dx plus, if you want all this, sorry, equals 0. All that equals 0. So plus r integral from minus infinity to infinity ut squared dx equals 0. But look, this thing in brackets was precisely the energy. So that's d over dt e of t, or in other words, e prime of t. Okay. And we get that it equals plus this term equals 0, so it equals to minus r integral from minus infinity to infinity of ut squared dx. Now, what is the sign of this? Notice, this thing is positive because we have a square, or at least non-negative, and this is positive, I think, by assumption, so this whole thing is less or equal to 0. So what have we shown? The derivative of the energy is something less or equal to 0. So e prime of t is less or equal to 0, and by math 2a, you basically get that the energy decreases. How cool is that? All right, any other questions? Already a bit over time, but if there are other questions, let me know.